Okay, here we go. So, 481 through 84. Actually, that's what we're doing here. I should say that first. This is 81 to 84. She did not. What? It has nothing to do with AP chemistry.
I know, but I still Anna's name. I had to.
So 81 to 84 is just, again, it's complete review, although it's the first couple of sections are a little more in depth than you're probably used to, and we're going to talk about this more. So you have a lot of practice problems to do with this stuff. The good news is most of it's going to be pretty familiar to you already, I think. I hope. But Section 8.1 basically talks about chemical bonds, ionic bonds, so chemical bonds in general, and then it talks specifically about ionic bonds, covalent bonds, and it mentions metallic bonds. We're not really going to talk about that until we get into solids. So basically, we're going to talk about the different types just a little bit, and how those different types work, and how, of course, they're related to Coulomb's law, because that's all we ever talk about in here is Coulomb's law. So it mentions Lewis symbols a little bit. It mentions the Octet Rule, all of that good stuff that we talked about last year, right? Octet Rule is that, in general, atoms want to have a noble gas electron configuration, which is typically 8 valence electrons, right? You guys remember what the valence electrons are? Like when we're talking about electron configuration. So if I write an electron configuration like this, I'm going to do a hard one here. Okay, how many valence electrons does that particular element have?
5.
Almost. Okay, remember the valence electrons, that's the sum of the highest energy level S and P electrons, right? So these are valence when we define valence electrons typically. So it's 7. Yeah. So this would be a halogen, okay? So that's kind of the idea with the valence electrons. Everything wants to have an outer configuration of S2 P6, you know, whatever it is, 4s2, 4p6, 5s2, 5p6. That's the most stable electron configuration because it's full s and p orbitals, okay? So that's kind of the idea as far as the octet rule. And then it goes into 8.2, it starts talking about ionic bonding. And the one thing that's going to be different in ionic bonding for you guys is lattice energy, the idea of lattice energy. Sorry, I think the ice cream truck is driving by or something. Anyway, the lattice energy is basically the energy that it takes to separate an ionic compound, okay, to separate two things that are ionically bonded from one another. All right? So where this is going to come in most of the questions you're going to see is you're going to see things like, let me think of an example here. So you're going to see things like, here's 2 ionic compounds. Which one has a higher lattice energy? Well, how are you supposed to know that, right? But it's actually not as hard as it looks, because if you remember Coulomb's law, then you can figure this out, okay? What charge does Mg have when it forms an ion? 2 plus, right? What charge does oxygen have when it forms an ion? 2 minus. What charge does sodium have when it forms an ion? 1 plus. What charge does chlorine have? 1 minus. So if you had to guess which one of those is going to stick together with a greater force, which one would be harder to pull apart, which one are you going to say? Yeah, the one that has the 2 plus and the 2 minus charge, right? Because that's a higher charge. So these things are probably attracted to one another with a greater force. Again, based on Coulomb's law, because that force is equal to the Q1 times the Q2 over the radius, right? With a constant put up in the front, okay? So because you would end up with a Q1, Q2 of 4 here and just 1 here, this one is probably going to have 4 times greater force, all other things being equal. Now, we got to think about this, the radius as well, okay? But for the most part, if you look at the charges here, then you'll be able to tell which ones have a higher lattice energy. And all that is just how much energy does it take to break them apart, okay? Does that make sense? That's the one major concept with ionic compounds that you're probably not as familiar with. So I would look in the book on that. They've got some good stuff in the book.
Ellensworth, Gilliland, and Whitehead contact the main office, please. What are you doing?
Okay. Sorry about that. So that's 8.2. Now 8.3 is covalent bonding. Okay. Covalent bonding, I don't know if there's a lot here that we didn't talk about last year. The main thing with covalent bonding is that's when we start drawing Lewis structures. Okay, you guys remember Lewis structures, hopefully? We did a lot of that last year. Yes? Please tell me yes. Okay, so when I draw the Lewis structure, for example, for H2O, yeah. Okay, so you just kind of have to remember how this works. Now, the way that I just did that, I know that there's one oxygen and 2 H's, okay? I know that H's can never go in the middle, right? You remember that rule? Okay? Hydrogens only want 2 electrons, so they can't go in the middle. So then I basically, and when you're drawing a Lewis structure, really, you'd probably make it like this because you wouldn't know the shape yet, necessarily, okay? And then we count up the total number of valence electrons that we have here. This hydrogen has 1 valence electron, this hydrogen has 1, and then the oxygen has 6. So that makes a total of 8 valence electrons that we have to work with. Okay? So you've got 8 valence electrons here. You have to put at least 2 in between each of the atoms to form the bonds in the first place. Okay? That leaves us with 4. So then the other electrons, you start putting them around the outside atoms first until they're all happy, except hydrogen's already fine, right? Because it only needs 2 electrons to have a configuration like helium. All right? So it's already got a full 1s orbital. It's good to go. So these other 4 electrons we can now put around the central atom to give it a full octet, and then you get your Lewis structure. Okay? And that's a very simple example. We probably need to do some practice on that again. So I've got a practice worksheet for that for tomorrow. It'll be fun. We might not even get to it tomorrow, but we should get to it on Monday. If we don't get to it tomorrow. All right, so then that's the Lewis structure, and then the bond polarity and electronegativity thing. That, I think you're going to remember also. The idea there, let's do something simple, because we're not talking about shape yet, okay? The shape, the VSEPR, the VSEPR stuff, remember when we did the gumdrops or the marshmallows or whatever we did last year? I can't even remember. Was it gumdrops? Yeah. How would you know they were awful tasting? You shouldn't know that. Did I? Oh. No, I let the record say that I did not say that anyone could eat anything in my classroom because that's against the rules. All right. Right, dispose of them. Yes, I meant, throw them in the trash. All right, anyway. So if you got something like, this is the example they give in the books. You've got a bond like HF, right? Hydrogen fluoride or hydrofluoric acid if it's dissolved in water. This is a bond, a covalent bond. They're sharing electrons right here, okay? This is also a bond, but they're different. How are they different? One has hydrogen. Okay. How are they different in the way that they're sharing electrons, I guess I should ask. See if you remember this. Well, no, the 2 fluorines are sharing electrons, okay? And so are the H and the F. They're both considered to be sharing electrons, but how is the sharing different between the 2 of those? Okay, yeah, it is different. I mean, different orbitals will be involved here. Okay, the two fluorides, two fluorines, I guess I should say, because they're not really ions here. The two fluorines are sharing them equally, right? You remember that? Okay, because fluorine and fluorine, they're really evenly matched in this electron tug of war, right? One of them can't pull the electrons any closer than the other one because they both have the same electronegativity. They both have the same size nucleus, the same ability to pull the electrons themselves, okay? So this is a completely equal sharing, all right? We call that a nonpolar covalent bond. You guys remember this? Okay. H and F, poor hydrogen can't pull as hard on the electrons as fluorine. Actually, nothing pulls as hard on electrons as fluorine does, right? Because fluorine's really small, and it's got a big nucleus for its energy level, right? So basically, the way these are going to be shared, kind of more like this, right? They're sharing, but the electrons are being pulled a lot closer to the fluorine than they are to the hydrogen, okay? So that bond, really, this side is going to be a little bit more negative, and this side is going to be a little bit more positive. Now, I shouldn't put an all-out negative or positive there, right? Do you remember how we showed a partially positive or a partial negative charge? Yeah, it's a soup ladle, right? So this is a soup ladle negative, soup ladle positive, okay? And that is what we call a polar covalent bond. Okay? Now, I don't know if you remember us talking about this, but this is really on a continuum, right? So then eventually you're going to get over here to the other side where you've got something like sodium chloride, okay? And these electrons really, the difference in electronegativity is so big there that we don't say that they're sharing at all. We say that really the chlorine basically took the electron away from the sodium, right? So now this has a full negative charge. The sodium has a full positive charge, and we call this ionic. All right, so there's your continuum. You've got your nonpolar covalent. You've got your polar covalent. And then you've got your ionic, okay? Now, I think we talked very briefly last year about the electronegativity difference. If you actually calculate the difference between them, then a range of about 0 to 0.4 difference would give you, we would consider that to be nonpolar covalent. A range of about 0.4 to somewhere around 2. Somewhere around 2 would be a polar covalent. And then anything greater than 2 we would call ionic, okay? You don't really need to worry about those values for the AP exam. They don't give you electronegativity values on the exam unless they give it to you within the question itself, but I've actually never seen them even give you one of those. What they want to know is that you can look at the periodic table, and based on the trends, you can kind of tell if something's going to be ionic, polar covalent, or covalent, all right? So perfect example, anything that's diatomic, like F2 or N2 or H2 or O2, any of those things, that's going to be nonpolar covalent, right? That's really easy. Anytime you have two nonmetals combining with one another, that's probably covalent, right? You guys remember that from last year? Or we've even talked about that this year. Any of the blue ones up there that combine, like nitrogen and oxygen or sulfur and chlorine, that's going to be a polar covalent bond typically, because there is a difference in electronegativity, but it's not that great because they're both nonmetals. Anytime you have a metal and a nonmetal combining, that's typically going to be ionic. All right? And that's basically the trend that they want you to know. Does that make sense? Okay.
Is there any other way to get a non-polar covalent bond?
Besides a nonmetal and a nonmetal?
No, the non-polar one.
Oh, the nonpolar ones. You know, carbon and hydrogen are so close in their electronegativities that we usually consider that to be nonpolar covalent. So any organic molecule that you have, where you've got this long string of carbons here with the hydrogens attached to it, we'll usually call these bonds nonpolar, okay? But there is a little bit of an electronegativity difference between them, okay? It's just so small that we say basically these are sharing equally, okay? But to get a perfectly non-polar covalent, you need two of the exact same atom for that to work, okay? All right, so I think that's probably what we needed to cover from the first 4 sections. Like I said, it's pretty much review. The lattice energy is the only thing that might throw you a little bit from these first 4 sections. And I think you're going to like the next 3 also, because that's basically just drawing Lewis structures, resonance, exceptions to the octet rule, all that stuff. And then once we get into chapter 9 is when we start talking about molecular geometry, all the super shapes and stuff like that. Okay? All right, maybe I will see you tomorrow, unless you're not here tomorrow.